Okay, guys, it's time to start chapter 26, fluid and electrolyte balance. This one will be divided into three parts, and we're going to start on part one right now. Homeostasis, this is all review from A&P1, but I'll go over it anyway. The negative feedback loop, if you guys recall, that's where when we call for something until we reach the level that we desire, and then we cut it off. It's kind of like a thermostat. If you set your air conditioner for 78 and it's 90 degrees outside, then as soon as your temperature inside your house reaches 78, it cuts off. That's negative feedback. When we reach the goal for which we're striving, then we stop doing what we're doing, which makes sense. If you think about it, you do that every time you pump gas in your car. As soon as that pump lets you know that it's full, you stop, because otherwise it's going to pour on the ground. So this homeostasis that occurs in our bodies, very important thing. A lot of people erroneously believe if something, a little of something is good, then more is better. But we know that there's actually very narrow ranges in which we need things. If we have too much or too little, it can cause really catastrophic consequences. When these levels are out of whack, when they go above or below, then this can actually affect multiple organs inside our body. Okay, let's break these up into three parts. We're going to discuss all three of these during this PowerPoint. The fluid balance is simply that the amount of water that we take in our food and in what we drink should equal the amount that we lose every day. If we want this to stay in balance, if we lose more than we take in, we're going to get dehydrated. If we retain more than we lose, then eventually the levels are going to build up and cause problems as well. We'll talk more about the specifics on that coming up in the PowerPoint. The electrolyte balance, we're talking about things like sodium, potassium, calcium, chlorine, all of these things. The amount that we take in through our GI tract should equal the amount that we lose in the kidneys, in the urine. Again, if this doesn't work out like that, if we have more than we need, then we're going to be in trouble. If we have less than we need, we're going to be in trouble. And then also the amount of hydrogen ions. If you recall, the more hydrogen ions you have, the lower the pH goes. And the lower the pH goes, the higher the acidity of the substance. If you guys recall, we were talking about the pH during the GI tract, and I told you the stomach pH is somewhere on the order of 0 to maybe 1, and absolutely completely neutral, neither acidic or alkaline, such as exactly pure water has a pH of 7. Anything a pH of 6 is going to be 10 times more acidic than a pH of 7. The pH of 5 is 10 times more acidic than 6, so that means it'll be 100 times more acidic than 7, and so forth. Okay, as far as our body water content, we got two little things here. So the amount of water that's stored with fat is 20%, which is not surprising because fat and oils and water do mix. The amount that is stored with the muscles, meaning these are proteins charged, is 75%. As a rule of thumb, infants have 73+% of their body weight as water. People who, as they age, it goes down, it can go down to 45%. Now, for the average adult healthy male, 60% average adult healthy female 50%. We'll talk about why that's so in just a few minutes, guys. And the amount is going to change, obviously. You're going from an infant to an adult and then eventually to an elderly state. Balance is so important. Things have got to stay in the proper proportions. So we have different compartments. We have compartments that would contain water. I'm going to go ahead and we'll jump right in. The intracellular fluid, ICF. Intracellular means this is inside the cells of your body. There's approximately 25 liters of water inside the cells of the body. About 40% of the body weight of a healthy adult male is going to be the water that's inside the cell. Now, we have waters that aren't inside the cell. We have waters that are outside the cell. These waters that are outside the cell, about 15 liters total. So for this average healthy adult male, about 40 liters of water. 25 inside the cells, 15 outside. Now, outside the cells, there are two compartments, subcompartments if you like. We have one that we call the interstitial fluid, and we have one that is in the blood vessels. We can call that the plasma. I'm just going to abbreviate that. So of that 15 liters, about 12 liters is going to be tissue fluid or interstitial fluid. 3 liters of that 15 is going to be in your blood vessels. So about 80% of the water that's in the extracellular fluid, the ECF, is going to be in the tissue fluid, and like 20% is going to be in the plasma. Okay? And since this is 40% of the weight of that healthy adult male, then both of these together will be 20%. Could you break it down further? Yeah, but that's really not necessary. So right here we have a picture. So there's water inside the cells, there's water outside the cells, there's water outside the cells and inside the blood vessels. Those are 3 water compartments. Here's where I tell you why males are 60 and females are 50. Females, adult females that have all of the secondary sex characteristics of the female, in general, are going to have more adipose tissue. There's adipose tissue around the hips. There's a lot of adipose tissue in the breast. And it's because of that. You remember where I told you that 20% of the adipose tissue is going to be water, whereas 75. So the very slight differences in the amount of muscle and versus fat tissue is going to account for the differences between the male and the female. Okay, we've talked about these compartments. What we haven't talked about is water can move from one of those compartments to the other. We've done the blood vessels, so we know that fluid can move outside of the capillaries on one end and move back in on the other end. So diffusion, which is the movement of solutes, particles like sodium or whatever, osmosis, which is the movement of water, and then the carrier-mediated transport are going to be responsible for the movement of this. Well, what does diffusion have to do with the movement of water? That's osmosis. Well, remember what I told you during the renal chapter. If sodium moves, it's going to move water with it. Water's going to follow. Water follows salt is our rule of thumb. That's a little bit too detailed for us. We're just going to leave it with this one is actually has different numbers. Let's just stick with the numbers that we have. The I think that's going to be sufficient for our purposes. Here's another showing the plasma 3, the IF 12, the ICF 25. Electrolytes and non-electrolytes. Oops, didn't mean to do that. I think I need to move it a little bit. There we go. Okay. Okay, non-electrolytes. These are chemicals that are covalently bonded. If you may have to reach back into your A&P1, you may have to pull out your notes or your PowerPoints, whatever. But covalent bonds generally don't break apart when they're in fluids. Things like glucose, sugars, lipids, creatinine, urea, these guys are sharing electrons, and they generally don't break apart unless there's a lot of energy applied. Well, there's actually a release of energy, but in any case, non-electrolytes generally are not going to come apart. So all the carbons and hydrogens and oxygens in glucose are not going to dissolve into water. Electrolytes, on the other hand, they're going to break apart. The electrolytes down here, they're showing sodium chloride, just regular salt. These guys, if you remember ionic compounds, these guys actually transfer an electron from one atom to another. Sodium has one electron too many. Chlorine has 7, it needs 1. So the solution is for chlorine to take sodium's electron. Sodium is now stable, chlorine is stable. Sodium also now has one more proton than it does electrons, so it has a net charge of +1. We generally don't write the 1, we just write the sign. Chlorine now has one more electron than it does protons. It has the -1. These guys are not sharing an electron, and they are actually only bound together by the electrical attraction between opposite charges. But as soon as you put these guys in water, water has partial charges. These guys will dissociate. Their bond between themselves will go away, and they will bond with some of these water molecules. I'm giving you kind of a rough and ready review of that chemistry. You can see more about it in your A&P1 materials. So anyway, there's our electrolytes. And why do we call them electrolytes? Because they are charged. These are ions. There's molecules like sugar. It's dissolved in the water in that the individual molecules are no longer associated, but the molecule itself does not break up. And that's our non-electrolyte. Here's the difference between compound solubility. Something that's very soluble, whether it's an ion or what have you, is going to break up very easily in water. Something that's low will have some breakup, but mostly it will not, as you can see in this one. Electrical conductivity. This guy has none because he's covalent. These guys haven't broken apart. Strong and weak depends on how easy it is for these guys to come apart. Some things like hydrochloric acid, HCl, these guys break apart real easy. Almost totally, 100% come apart. So that's going to have a strong conductivity. These guys here, maybe like a weak acid, like acetic acid or carbonic acid, it's going to come apart, but it's not going to be as many, so there's fewer electrical charges capable of moving. Edema, it's where you get excess fluid in the extracellular space, usually from the plasma. That's what's going to be the main cause of it. So you have extra fluid that comes out and isn't reabsorbed back into the blood vessels. Things that speed up the flow of fluid, like excess pressure on the fluid, or things that keep it from returning to the fluid, can cause this. Some of these things include incompetent venous veins. If the blood is the vein valve fails, then the blood is going to flow backwards. And the more blood you have in the same area, the greater the pressure. The greater the pressure, the greater the movement of fluid. If a blood vessel is blocked, congestive heart failure, blood backs up. If you have a high blood volume, if the lymphatics are blocked, like we had discussed when we did lymphatics, when I was telling you about how that used to be a very common thing in breast cancer, to see the arms swollen because of the removal of the lymphatics and the blockage. Increased hydrostatic pressure, which is blood pressure, or permeability. One other thing can cause this is if your albumin, the protein that gives you the oncotic pressure that helps to keep all the fluid in our blood vessels, excuse me, if you have some sort of liver problem and the albumin levels are low, you'll have less power pulling the fluid back in, so you'll have more that leaks out. Swelling or this edema caused by infection or injury. I mean, everyone I think has probably had some type of swelling associated with inflammation, and that's basically, it is edema. Major cations and anions in each compartment. Again, this should be a review for you guys, okay? We're going to hopefully see it that way. Okay, let's talk about the red compartment, which is going to be our excuse me. We have about 140 milliequivalents per liter. Only thing you really need to know about that is it's just a unit of measure. So 140 is going to be in the blood plasma. As far as the potassium levels in the blood, it's going to be very low right there. As far as the bicarb, it's going to be maybe 25 in the blood. Chlorine levels are going to be over 100, about 105, 110. Hydrogen phosphate, not very much. Sulfate, not very much. And then the proteins, not very much. Now the interstitial fluid, remember that's the tissue fluid, you're going to see the levels of sodium very close to what you have in the plasma. Same thing with the potassium. It's going to be way lower than sodium, very, very low. Calcium levels are going to be fairly low too. They're going to be fairly equivalent though. It's just a very slight difference. Same thing with magnesium. Bicarb levels are just going to be just a smidgen higher. Chlorine levels are going to be a little bit higher in the interstitial fluid. The phosphate or hydrogen phosphate, the sulfate, all of this, they're more equivalent. Now, one thing though that's not is if you notice the amount of proteins that's in interstitial fluid is way low, especially compared to the plasma. But the plasma needs its proteins, like the albumin I just told you about, in order to keep the fluid inside the blood vessels. So for the most part, the blood plasma and the interstitial fluid are roughly equivalent. Now this is where we get the very big difference, and that's going to be in the intracellular compartment. There is not very much sodium inside the cells. However, the potassium levels are super high compared to all the rest. No calcium in there to speak of. I know there are muscle cells that have them. Magnesium levels considerably higher. Bicarb levels not so much. The chlorine not very much. Chlorine is definitely an extracellular anion. The hydrogen phosphate levels, though, are considerably higher. Sulfate. And then the protein levels, believe it or not, are higher inside the cells than anywhere else. Kind of makes sense. We have a lot of things, structural enzymes and all of this inside the cells. So one thing, and this is again, this is an AMP1 topic, and I hope you guys learned it there. Sodium levels are way high on the outside of the cell. The potassium levels are going to be way high inside the cell. Okay? Regulating fluid and electrolytes. Let me get all my stuff separated so we can do that. I can hardly see this. It's kind of small. So this is what happens. As far as maintaining, we talked about the very first slide, how everything needs to be adjusted and be in balance. But we don't actually control the adjustment for the intracellular fluid. We adjust the ECF. And based on that, we'll have movement occur between the ECF and the ICF, between the cells and the outside, the extracellular environment. We don't have any receptors that directly monitor either the fluid or the electrolyte balances. And this is kind of important. We don't move water out of our cells by active transport. We don't use ATP and push it out. The content of the water and the electrolytes will rise. If you take in more than you lose, it's going to fall if you lose more than you take in. Okay, right here we've got low blood volume. So we don't have enough blood, and this is going to be mostly because the blood is mostly water, the plasma. That's going to cause the concentration of the sodium to go up. This is going to be monitored by the hypothalamus, which is going to stimulate our thirst center to let us know that we're thirsty. We're also going to get ADH released. Those things that I really don't like this one. Let's go into the next one. This one's too small. It's hard to see. We will talk about this, guys. Let's just do it on a different one. Gains. How do you take in fluid? You get it from your eating, drinking, and remember we get a little bit of it from metabolism. We make water at the very end of the electron transport chain. Where do you lose it at? There's a certain amount in urine, feces. You also have insensible loss. This is both going to be from the skin and out the lungs. When we breathe out, there's a certain amount of water vapor in our breath going out. We also have insensible perspiration, where we lose it through our sweat glands, but they never beat up. That's why it's insensible. And then, of course, we have sensible perspiration, which is where we're going to lose it through the sweat glands, but we will be able to tell it. So, average daily intake, 2,500 milliliters, 2.5 liters. We're going to get about 10% of our water just from our making ATP. Our foods are going to give us about 30%, or about 750 milliliters. And then the fluids that we drink are going to give us the balance of that, about 1,500. As far as our loss, there's a certain amount, even though the colon is there to maximize the absorption of water, some of it has to go out in order not to have dry feces, because that would be a very uncomfortable process. There's 8% when we have actual sweat, and you can see the actual the volumes. The insensible losses from the skin and the lungs, about 28% of the water. And then about 60% or about 1.5 liters goes out every day in the urine because we need a certain amount to flush it out. Water balance, water content of fluid. This is basically the same thing. They're using slightly different numbers, but that's okay. I'm not going to ask you questions on numbers. It's just kind of an approximation. So if I were to ask you something, I would ask you where is the majority of your fluid intake from, and you would say the beverages, 60%, more than half. And if I were to say, where do you lose most of your water at? You lose it through the urine. Things like that, guys. I'm not going to ask you to memorize these numbers because obviously they change. Water balance through the negative feedback. Here's where we're going to talk about that stuff that we talked about before that I couldn't see. Okay, the ECF osmolality goes up. And again, let me draw a little something. If I had a 5-gallon bucket from Home Depot, and I put a pound of salt in there, okay? I've got 1 pound of salt in 5 gallons of water, okay? So that's like a 1:5 ratio. What if this bucket was only half full, but I still put a pound of salt in there? Then I would have 1 pound of salt in 2.5 gallons. Can you guys see that this salt is twice as concentrated? Because I've got the same amount of salt, but if I don't have as much water, it's concentrated. So the actual concentration here is one pound per 5 gallons. Here, if you were to do it on the same 5 gallons, you would say this would have a ratio of 2 pounds per 5 gallons. Because to get that to 5 gallons, you'd have to multiply everything by 2. So that's what we're talking about. This can happen in a lot of ways. So the osmoreceptors, these are guys that are monitoring the concentration of these electrolytes. Again, they're going to go to the thirst center. It's going to make you think that you're thirsty, wants you to go and get water. We're going to decrease the amount of saliva. We're going to have a dry mouth because we're trying to conserve it. Because if we're low on water, then the priority is to keep it into the blood vessels. When we have that sensation and we actually take a drink, we're going to moisten the mouth and the throat. It's also going to stretch the stomach and the intestines. And remember, we've got the enteric nervous system there. The water is going to come in through the GI tract. And when it happens, I'm going to add more water. It's like I had this half-gallon bucket right there. How could I take, let's just use the same original. How could I change that to make it less concentrated? Pour 2.5 more gallons of water in, right? And that's what we're doing here. We're adding more water, and when we do that, we're decreasing the concentration ratio. Now, this is negative feedback, so this guy, all of this is going to go to the hypothalamic thirst center and let you know you are no longer thirsty. You're good. So there's one way of monitoring our water balance, and this is a negative feedback loop. It's pretty simple. If you're thirsty, you're going to drink, and when you've drank enough water, then you're going to turn off the thirst center and say, okay, I'm good. Okay. Now, if the amount of our blood, remember we had 3 liters, if that changes 5 to 10%, that's going to be 0.15 to 0.3 liters, then our blood pressure is going to decrease because of the lack of fluid. Those cells in the kidney in the JGA are going to detect that. They're going to start that renin, angiotensin, aldosterone thing. We're going to have the angiotensin 2. The angiotensin 2 is also going to stimulate the hypothalamic thirst center. This decrease in saliva in that dry mouth also is going to stimulate it. The low blood pressure itself will stimulate the hypothalamic thirst center because we've got baroreceptors monitoring our blood pressure. So all of these things are going to be the ways that the body is going to be able to monitor your fluid balance. And when it gets low, it's going to make you thirsty and also make sure that you don't use a lot of water when you eliminate those metabolic waste during urination. Regulation of water output, that's the renal. We've already done that, but we'll review it because I know it helps you guys to review this stuff. So about 1.5, depending if the size of the person, could be 2 liters a day. Also depends on how much water you drink. The more water you drink, especially more than you need, the more urine you're going to put out. Which is what the second point is. We're going to adjust our output depending on how much comes in. Remember, we're wanting to keep things at a certain level. If you take in too much, then you're going to put out more. If you don't take in as much, then the amount you take that you put out is going to decrease as well. We want to rid ourselves of excessive salt, creatinine, urate, and urea. This stuff, those metabolic waste that we need to get rid of, but we want to use the minimum amount of water. ADH, this is a review back from, well, we talked a little bit about this in the renal system. We've talked about it in the endocrine. We'll go ahead. So we've got osmoreceptors in the hypothalamus. They're monitoring the ECF. We've already said that. If we have increased concentration, usually due to decreased water, like on my bucket analogy, this is going to cause the ADH to be released. This is going to cause the arterioles to constrict, which is going to maintain our blood pressure. And in addition, you remember the collecting duct, we're going to have these cells that are going to have aquaporins that are going to be placed on them on both sides. And that's going to facilitate the movement of water from the collecting ducts back into the ECF, where it eventually will make its way to the plasma. And you see with all those aquaporins there, how much more water you reabsorb. Okay, our negative feedback loop on here again, this is really a lot to do with the endocrine system, but it doesn't hurt to review. Increased osmolality, increased sodium concentration. Osmoreceptors pick up on that, going to the posterior pituitary where it's going to release ADH. And we know it's going to go to the collecting ducts, going to increase water reabsorption. The more water we reabsorb, we're going to have less urine, scant urine. Never heard that term, but okay. And the more water we bring in, the more we increase the amount of fluid in the plasma. And as we increase that, we're going to cause the concentration, the osmolality, to go down. Again, you remember my little bucket illustration. How do I take care of that high concentration in that 5-gallon bucket? Put 2.5 more gallons of water in it. So I just need to add more water to correct this. And that's what we're doing through the kidneys. And plasma volume, we talked about that. And the baroreceptors, the pressure sensors in the atria and in the aorta are going to pick up on that, and they're going to stimulate the posterior pituitary again to release the ADH. Okay, guys, diuretics. We did talk about this. Ooh. Oh, okay. Oh, I lost my pen. How about that? Okay. Diuretics, we did talk about that a little bit when we were doing the renal. We give diuretics, especially when someone is fluid overloaded. They have too much fluid, and we want to get more fluid out, especially in people with congestive heart failure. This is a problem. Diuretics are going to block the normal reabsorption mechanisms in the loop of Henle and cause us to put more out. We talked about the thiazide diuretics and the DCT. We talked about the potassium sparing diuretics that are going to try to keep from um, reabsorbing sodium, because if we reabsorb sodium, we have to put potassium in its place in the DCT. And we talked about the loop diuretics, which are going to block the reabsorption of water, oh, excuse me, not water, but the sodium on this side. And by having more sodium remain inside the loop, then more water will also go out. I don't really think there's much point in Lasix as a loop diuretic, but we don't need to go into that. Other things that act as diuretics, alcohol. People who drink are famous for spending a lot of time in the bathroom because ethyl alcohol decreases, inhibits, keeps the brain from releasing the ADH. Caffeine is also a diuretic. Caffeine will make you go to the restroom a lot. People who drink a lot of coffee or sodas or anything like that. Okay, fluid movements. Let me get my thing down here. Hydrostatic osmotic pressures. We talked about that with the capillary. And I'll show you again in just a minute that process. Exchanges between the plasma and the interstitial fluid across the capillary walls. And then exchanges between the interstitial fluid and the intracellular fluid is going to go across the plasma membrane. And remember, water can move across the plasma, even though it's charged. It is so small it can move through the plasma membrane without a problem. So this is the take-home message, guys. Your concentration in the extracellular fluid is going to determine how much you're going to have in the ICF. I'm going to go ahead and do this. So now I have a cell, and there's the ICF in there. Everything is normal. We've got like a 300 milliosmol inside, and now here's the ECF. What would happen if I had diarrhea or vomiting or urinated too much, diabetes insipidus, and I got dehydrated? If I get dehydrated, then the amount of water in the ECF goes down, and the amount of osmolality of the sodium goes up. By definition, if this is 300, and let's call this 350 or something, I'm dehydrated. I have more sodium out here than I do water. Here I'm in normal. Water is going to move out of that cell until these guys are in balance, equal. That's osmosis. Again, this should be a review for you guys from A&P 1, but just in case, I'm trying to give it to you right. So if I have a higher concentration, I can say that this ECF is hypertonic. Okay? That's what we're saying. The ECF is hypertonic, and because of that, water is going to move out. What's going to happen to this guy? He's going to shrivel. He's going to, the technical term is crenate, C-R-E-N-A-T-E. That's how the ECF. What happens, let me try to back up enough so that I can try it again. What happens if the situation is different? What if I've got too much fluid out here? What if instead of 350, it was 250? And this guy's still 300. Well, how can I get that to 250? I have more water than I normally do. So what's going to happen now? Well, instead of being hypertonic, this guy is now hypotonic. I'm just going to leave it there. So that means there's a bigger concentration in here. Water's going to move inside. What's going to happen to this? Well, depending on how much water, if enough water moves in, it's going to go pop. That's what we mean when we say the ECF solute concentration is going to determine water is going to move into the cell or out of the cell depending on the concentration of solutes in the ECF. Okay, Starling's law of capillaries. Water circulates continuously within the ECF. The hydrostatic pressure at the arterial end and osmotic pressure at the venous end regulate the movement. And if this guy changes in any way, it's going to change where the fluid is. Okay. Here, not going to put any numbers. Remember, we got the albumin on the inside. The albumin can't leave. It's too big. So say I've got a pulling force of 25 mmHg because of the albumin. That's not going to change. It's going to be 25 over here too, because these things aren't leaving the capillary. Now, let's say that the blood pressure there is 35. So the blood pressure is pushing outward. The oncotic pressure of the albumin is pulling inward. So if I got 25 pulling inward and 35 pushing outward, what's going to happen? Some stuff is going to move out because of that 10 millimeters of mercury difference. We did cover this on the blood vessel. You can check your notes on that to refresh yourself. Now, by the time the blood gets to the venous end of the capillary, what's happened? Well, I'm making these numbers up, by the way, just to illustrate my point. Let's say the blood pressure is now 15. Now let's make it 17. We go 17. This is still 25, so now I've got a difference of 8. That means I'm going to be pulling water in because the pressure to push out has been used. The pressure or the pulling power inward is still available. That's Starling laws. This is what moves the fluid in and out of the capillaries. Alterations, if your blood pressure is extra high, you're going to push more fluid out, right? Because these guys are, for our purposes, unchangeable unless you got something going on with the liver and your albumin is not functioning or you don't have enough. But if the hydrostatic pressure, the blood pressure goes up, you're going to push more water out. That's just all there is to it. Okay, hypertonic, hypotonic. So there these guys are in balance. You've got the right amount of fluid in both compartments. Water loss from the ECF, and I'm just losing water. I still have all those particles there. I'm going to move water out here. But if the But if I have more water here, oh, I'm sorry, they're still doing that. That's just showing you the movement in. But if, again, as I said, if it is more dilute outside than in, then water is going to move in to the cell. Dehydration, there's a couple of ways you can do this, but you're losing more water than you're gaining. Sweat a lot, yeah, if you work in a hot environment where it gets extremely hot and humid, you can dehydrate easily. Not drinking enough water, obviously. Vomiting, diarrhea, you lose a lot of fluid there that if you don't replace it, it's going to tell on you. It's going to cause the ECF to become hyperconcentrated or hypertonic. I'm trying to see what this promotes water loss and excessive electrolyte loss. Okay, so if you're losing water more than you are, say, sodium, then that's going to affect the concentration. So let's give an example. Someone has diarrhea. They lose a liter of, let's make it 4 liters of water. They're in serious shape. But they're not losing any sodium, so their sodium concentration is going up. That's called hypernatremia. You know, sodium's abbreviation is Na, natremia. This is going to cause our ADH. We're going to get the renin out, and because of the lower blood pressure, and we're going to get very thirsty. This is something that is really bad. You can also get hypotonic from drinking too much water very quickly. A few years ago, there was a radio station on the West Coast that had a water drinking contest. There was a woman who won that water drinking contest and then died from water toxicity. Okay, there's my 5-gallon bucket. So what if I've got that half full, but I only have a half a pound of salt in it, right? Well, that's a half a pound to 2.5. So that's the same concentration as 1 pound in 5 gallons. Well, what if I add the other 2.5 gallons? What I have effectively done is I've changed the concentration down to 1/4 to 2.5. So I have actually got hyponatremia. This is going to, because of this is going to be hypertonic, remember what the osmosis, the water is going into the cells, going to cause them to swell. Nausea, vomiting, muscle cramps. Please note, cerebral edema, your brain is going to swell. This is damaging to neurons. Disorientations, convulsions, coma, and death. A lot of marathon runners have died. That's why you get those drinks that have the electrolytes. You're adding water, but you're also adding sodium with that so that your electrolytes don't go out of whack. Hypernatremia or hyponatremia both end. All of this, I mean, you get this from either one. Very critical. Electrolyte balance, sodium, potassium, chloride, bicarb, calcium, phosphate. We get it through the GI system. We eliminate it through the kidneys, some in the sweat. Our sweat is salty, some in the feces. And then we adjust things in the kidneys and in the lungs in order to maintain those levels. We'll talk more about those in the later PowerPoints. Okay, here is a reference for the electrolytes and the other things. You do not need to memorize these guys. These guys are going to be different depending on which lab, because different labs use different techniques, and therefore the normal range will be different. In general, that's pretty good, 3.5 to 5. On potassium, 135 to 145, but nobody has to memorize these ever, okay? Liver function test, ALT, AST, they actually call that one ALP. These are enzymes, kidney functions, BUN, creatinine. There's our albumin. It's usually around about 4. If it gets down to 2, you're going to get a lot of edema. But we'll just focus on this. We do check the urine for sodium, potassium, chloride, calcium and phosphate. You have to do a 24-hour collection because it's going to vary. And bicarb usually doesn't go out in the urine. Well, guys, that's everything for part 1, and I'll see you in part 2.